We're now going to start section 8.6, where we will talk about the dot product and its uses. In the last section, we introduced several different vector operations. In this section, we introduce one additional operation known as the dot product. The dot product is defined as follows. Given two vectors u and v, the dot product, and we want to note that this is how we represent the dot product with the dot in between the u and the v. And we find it using this formula. Now, this formula is very easy to work with. Essentially, what it tells me is to take u sub 1 and v sub 1, which would be the first two components, and multiply them together. And then take the second components and multiply those together, and then add the result. And so we're going to look at a couple of examples, but once we see how this works, calculating the dot product is fairly straightforward. Okay, so we have three quick examples that we're going to do here. Our first vector has the representation -5, 2, and our second vector has 3, -1, and we want to find the dot product of that. So remember that you're going to take your first two components and multiply them together. So we're going to be doing -5 times 3. And then we're going to do our second two components. So that would be the 2 and the -1. And we're going to multiply those together. And when we get the multiplications done, we're going to add. So -5 times 3 is going to give me -15. And we're going to be adding that to 2 times -1 would be -2. And so we're going to end up with a dot product of -17. In some books, they refer to the dot product as the scalar product. And we do that because when we multiply the two vectors, it turns it into a number. Okay, let's look at example B. We have a vector represented by -5, 2, and a second vector represented by 2, 5. And we want to find the dot product. So we're going to multiply our first two components. So -5 times +2, that's those. We're going to multiply our second components, which would be 2 times 5. And we're going to add in between. And so -5 times 2 is -10. 2 times 5 is +10. Adding together, we have a dot product of 0. And finally, for our third example, again, multiplying first components together. So that's going to be -5 times -5. Our second components would be 2 times 2. And we're adding together. So we're going to have -5 times -5 will be +25. 2 times 2 is going to be 4. And so our dot product will be 29. Now we have some basic rules that apply for dot products. The first rule essentially says that it doesn't really matter in what order you do the dot product, you get the same result. So u dotted with v is the same thing as v dotted with u. We have a rule that says if we do a dot product with a 0, the result is 0, and that makes sense. That's basically the same as multiplying a number by 0 and you get 0. We have essentially number 3 being like a distributive property where we can distribute our dot product among a parenthesis. Here we have as number 4, we have a times the dot product is going to be the same thing as a times vector u dotted with v. Or you could do u times a times v. And then the fifth one says that if you take the dot product of a vector and itself, that it's equal to the magnitude squared. And so we're going to look at an example using this, and we'll come back and use some of the other ones at another point in time. All right, so we have an example that says, given that the dot product of a vector u with itself is 8. Okay, so what that means is the dot product of a vector u with itself. So this is the dot product of a vector u with itself. And we know that that's equal to 8. And we're trying to find the magnitude of vector u. Okay, so what we're going to use here is we're going to come back and use this number 5 that says that a vector dotted with itself is equal to the magnitude squared. So let's go back to our example. I'm going to write that down just so I don't forget that rule. U dot product with itself is equal to the magnitude squared. And so what that tells me is that I know that the vector u and itself is equal to 8. And so essentially what we have is this part right here equals 8. And we know that that's going to equal to the magnitude squared. Okay, so what can we do? How can we get from the magnitude squared to just the magnitude that we need to answer the question? And so we know that we could come in and take the square root to get rid of that squared. And so the square root of 8, remember, is going to be 2 on the square root of 2. And taking the square root of the magnitude squared is just going to leave me the magnitude. All right, and so our final answer here will be 2 on the square root of 2 for the magnitude of vector u. We also have a theorem that says that if we have two vectors, u times v, and theta is the smaller of the two angles formed by u and v, then this statement is true. The dot product of u times v is equal to the magnitude of u times the magnitude of v times cosine theta. All right, and a lot of times we will see this theorem being used to solve for the angle. So let me go ahead and show you kind of how this is going to work. We're going to take this right-hand side and I'm going to solve it for a cosine, which means I'm going to divide both sides by these two magnitude values. And remember, we know that if we do it to one side, we also need to do it to the other. And so what that gives me is an expression for a cosine, because everything's going to cancel, and we'll have cosine equaling the dot product of u and v over the magnitude of u times the magnitude of v. All right, so let's go ahead and look at an example and see how we use that theorem. I'm going to very quickly write down what we had on the other screen. We had that the cosine of the angle was equal to the dot product of u times v divided by the magnitude of u times the magnitude of v. All right, so our directions here ask us to find the angle, find the theta, between vector u, which is -3, 1, and vector v, which is 2, 5. So let's go ahead and sort of find the different parts that we need. One thing that we need to find is we need to find the dot product of u and v. So I'm going to go ahead and do that. Remember that that means that we're going to take our first components and multiply them together. So -3 times 2 is going to give me -6. And then I'm going to take my second components, the 5 and the 1. I'm going to multiply those together. 5 times 1 is 5. And we're going to add. So my dot product is going to be -1. I'm also going to need to find the magnitude of vector u. Remember, the magnitude is found by taking your first component and squaring it, added to the second component and square it, and then taking the square root. So -3 squared is going to be 9. 1 squared will be 1. And so the magnitude of vector u is going to be the square root of 10. We also are going to need to find the magnitude of vector v. So I'm going to take my first component, which is 2, square it, add it to my second component, which is 5, and square it. 2 times 2 is 4. 5 squared is 25. And so the magnitude of vector v will be 29, the square root of 29. Okay, so once we know that, then we can go ahead and come back to our problem and plug in those values. So I'm going to have that the cosine of angle theta is equal to the dot product, which we found to be -1, over the magnitude of u, which we found to be the square root of 10, and the magnitude of v, which we found to be the square root of 29. Now, just for the sake of making this a little bit easier to go to my calculator with, I'm going to go ahead and combine these two square roots. 10 times 29 is 290. Okay, and then we're going to enter it in our calculator. Now remember that we're looking for an angle. So in order to find an angle, recall that you use your inverse cosine key. And so I'm going to put my calculator in degrees. I'm going to do inverse cosine of -1 divided by the square root of 290. And you should come up with 93, and if we're rounding to 1 decimal place, 93.4 degrees. Okay, and that would be the angle that lies between the two given vectors. Another theorem that we have that is going to hold here says that if we have two vectors and we do a dot product, then and the dot product is equal to 0, then that means that the two vectors had to be perpendicular, or another way of talking about that is to say that they are orthogonal. So our example here asks us to find a vector that is perpendicular to the vector 7, -2. So remember that we essentially need a vector that when we do the dot product of that, we end up getting 0. So there are lots of different answers here. One answer would be the vector 2, 7. Okay, and I know that because, and I'm using these same sort of values and switching them around a little bit, but look at your dot product when I do that. If I do u dotted with v, and I multiply my first two components, so that's 2 times 7, and then I multiply my second component, 7 times -2 would be -14, our dot product would be 0, and so that means that vector v at 2, 7 is orthogonal to vector u at 7, -2. Now, we can come up with lots of other answers. This is the one I came up with right there is probably the easiest one. Just to give you another example, we could use any multiple of our vector 2, 7. So I also could do, I don't know, let's see, I could do 4 and 14, and that would also work because when we do our dot product, 7 times 4 is 28, and 14 times -2 is -28, and that would also equal 0. So realize that on a problem like this, that there are lots of different answers that would be possible.